Okay, so we'll have a second lecture on probabilistic numerical computation. And if I just remind you about the ideas that we spoke about yesterday, was that we want to try to capture and account for uncertainty induced in numerical procedures. And this changes our view of the procedure from being one that is fully deterministic to one that is actually probabilistic. And in many ways, this is quite a natural way of thinking of the problem, because in essence, all that we are doing is putting additional mathematical structure in the space of functions. And that mathematical structure is induced by the probability measure associated with that space. Now, two of the things that I mentioned were potential advantages of taking a probabilistic view to numerical computation. Was that one, it could enable you to design new algorithms, which in actual fact would be provably and practically superior to existing numerical procedures. And so one of the things that I want to do today is actually illustrate that. The second advantage was that because we have accounted for uncertainty in our modeling process, we can then propagate that in a coherent and a consistent manner from a statistical perspective through subsequent computation. So in other words, if we have a pipeline of computations that we're going to be doing, that uncertainty can be propagated through each step of computation and can be done, as I said, in a coherent way. And so to illustrate that, we're going to look at an inverse problem. Now, inverse problems are classically defined as some sort of model of a process which there are certain components that we cannot observe either in total or partially. We make observations of the output of that process, and what we would like to do, and those observations, so that data is a consequence of the process being run forward and being observed. And what we now want to do is we want to employ the data, the observations, to invert the forward problem and make inferences about the things that we don't know. So, if you remember, we spent our time yesterday talking about the forward problem, which, if you remember, was that we had some operator, calligraphic A, acting upon our unknown function u, along with some boundary conditions and some forcing conditions. And the key thing that we do is that we put a prior probability distribution over our unknown class of function u. And that, of course, was a Gaussian measure because of the Hilbert space or the Banach space that these functions would reside in. And you had a very nice tutorial today on Gaussian processes. So all of the machinery that you need to solve these problems, you now have at your fingertips. But the key point here was that we defined a measure over the space of functions u. We observed data at a finite set of points, and the observed data was basically the evaluation of the right-hand side of the partial differential equation at a set of finite points. And then we just used Bayes' theorem to condition the prior measure of the observed values of g, and therefore we induced posterior measure for the function given all of the evaluations of g, and that is our posterior. And what I argued was that, you'll recognize these equations from this morning's lecture, tutorial. And the key point here was that the solution of the PDE, a numerical perspective, would be the approximation plus some approximations of bounds on the numerical error. The probabilistic solution is the posterior measure. It is the posterior probability distribution over the values of the functions at any particular points. That gives a far richer representation of a numerical solution because of the probabilistic semantics associated with that. So that's the forward problem resolved. We now have a probability distribution about our uncertainty in the value of the function u. And we can now take that probability distribution, which characterizes our uncertainty, and we can now take it to the next stage of computation. And the next stage of computation is going to be to use measured or observed data in solving the inverse problem. So what is the inverse problem that we're interested in? Well, if you remember, we had this very nice, benign, linear elliptic partial differential equation, and what was unknown was the value of the, we'll call it the diffusion coefficient or the conductivity coefficient, kappa, and kappa was some function of the location in the actual domain. So that's what we don't know. In the forward problem, of course, we don't know u of x, but we've already solved that. We now have a probability distribution over possible values of u. Now what we want to do is to fully solve the problem by solving the inverse problem and inferring the values of kappa that are supported by the observations that we have made. Now the key thing here, as I said, is that we have the forward posterior measure, right, pi of u conditioned on g, and we can incorporate this in the way that we solve the inverse problem. Now, where's my t? So let's do that. Now again, this is quite an unrealistic setting, but just for the convenience, for the pedagogy, so that you can grasp the basic ideas and the basic concepts without them being shrouded in technical details. Let's imagine that we have some instrument and it allows us to measure values of our function u of x. And we'll call these measurements y. So in the example of the thermal conductivity example, maybe we have made some measurements of temperature on the surface of the object at certain points. And those measurements would correspond to the yi's. But of course, the sensor that we use, the instrument that we use, will have some level of error, some level of precision, and that is represented by the associated with it here. And if we go to the manufacturer's tables, we see that in actual fact the error some distribution. So the good thing is that the measurements are going to be unbiased, but they are going to be uncertain. And so there is a certain level of variability in the measurements captured by the variance or the covariance gamma. Okay? So what that means is that the likelihood for the data under the model, okay, so the probability of all of the data from y1 to yn, conditional on what we don't know, which is going to be kappa. Now, if we took a deterministic approach, we would say, well, we've numerically solved our PDE, and so we have a solution U, so we will plug that value in, and we will ignore, I mean, it's difficult to know how you would convert a bound and an error into a probability, so without being ad hoc. So in the classic, in the sort of standard way, you would just assume that U is not a random variable and therefore does not have any uncertainty associated with it. In this case here, of course, we have a full distribution over the value of U. So it's random object. So given this distributional property on the sensor error, it means that the probability of our data conditioned on our unknown function and the diffusion, in this case constant, is going to be normally distributed around about the numerical solution for U, and it's going to have a covariance structure given by the covariance structure of the error. But let me emphasize that we don't know what U is. We know what an approximation of it is in the numerical, the non-probabilistic numerical setting, and in the probabilistic setting, well, we have a full probability distribution associated with it, and so therefore we can use that. And what we can do is we can take the posterior probability distribution for U conditional on G, and because that in itself is a Gaussian process, and because the likelihood also has a multivariate normal distribution, then we can integrate, or we can marginalize the effect of U, and so we can define marginal probability for the data conditioned only on the remaining thing that we don't know about, which is kappa. Okay, so this is just going to be a product of two normals, and we integrate with respect to this measure, which is a measure in U, and we get an analytic Gaussian marginal distribution for the data conditional on kappa, and it's equal to a normal for the data with a mean M1. And if you remember yesterday, the mean M1 is the mean of the conditional distribution for our unknown function given the evaluations of the left-hand side, and that corresponds to this mean here. And if you remember again, I made the point that this mean function is actually basically just the same as the numerical solution that you would obtain if you were to employ a symmetric collocation method. So that's the mean that we obtain. What's next? And the covariance structure now looks like this. The covariance is actually going to be equal to the sum of the covariance of the data error, right, and the covariance associated with the unknown function. So again, if we just go back to yesterday, then the probabilistic numerical solution of the PDE is this Gaussian process, which has a mean we've just described and has a covariance structure, right, which is defined here, where in essence the covariance is based on the covariance function of the prior plus the action of the linear operator and its adjoint on that covariance function. And what's kind of nice about this is immediately you can see that now the probability for the data given kappa is equal to this, and you can immediately see that the variance or the uncertainty now takes into account not only the uncertainty associated with the data, but the uncertainty associated with the numerical solution of U. So this is a very important point. If, on the other hand, we had just taken, NumPy and called a numerical solver for U, and then just plug that in here, then the total covariance or uncertainty would be that associated with the data only. Now we're taking into account the fact that we've got uncertainty not only induced by the data, but uncertainty induced by the numerical procedure that has to be employed in getting an approximate solution, or in this case, an estimate of the solution of the function that satisfies the PDE and its boundary conditions. So this is extremely important, because now we are accounting for this additional source of uncertainty. Now, what's important is that this is indeed something that is going to be statistically consistent. We know that as we gather more data, then the posterior for kappa given y, where we are not taking into account any uncertainty associated with u, so we're saying that u is given, or this here, we know that that will converge to a Dirac around the true generating kappa value, if there is such a thing as a true generating kappa value. This, of course, presupposes that we have complete belief in our mathematical model, that our mathematical model reflects reality in total. That will not necessarily, and in fact, most certainly is not the case. But if we make that assumption, and as we observe more data, then this posterior, right, so our uncertainty in kappa will start to shrink, and it will shrink to basically a Dirac on the true value of kappa that gave rise to the data from the model. If that is the case, then the probabilistic posterior induced by here. So in other words, what we would do is we would define a prior distribution for kappa to get the joint distribution for y in kappa, and then just turn the crank and get the probability for kappa given y. If we use that marginal likelihood, then we can show that it will also converge to a Dirac measure on the true generating value in the case where h, so h, if you remember, is the mesh size, or the level of discretization in the domain. If that decreases at a rate which is given by, well, clearly it's going to be dependent on n, the number of data observations, so the dimension of the vector y, and that's going to be raised to the power of minus 1 over, so again, if you remember, rho would be the order of the PDE, so in this case it's of second order. D is the dimension of the domain, and beta is the smoothness of the function class that we have assumed in the prior. And again, this morning's lecture spoke about, if you wanted a level of smoothness based on the differentiability of the Gaussian process function, then you would need to have two times that level of differentiability for the covariance function. And so this result really gives conditions that are required for the numerical method to ensure that the inverse problem will converge consistently to a Dirac on the true generating value. So this is quite important because it shows that the process is consistent, and it also shows that that on the way we are making a better job of accounting for all of the sources of uncertainty in our modeling problem. So let's just give an example. So if we go back to our little toy example, just to illustrate the point. So here, again, we're in the setting where our domain is just the unit line, 1D, and the boundary conditions are such that u at both 0 and 1, the extreme points of the unit line, are 0. We're going to say that kappa is equal to 1, and we're going to make observations of u at x equals 1/4 and 3/4. And those observations are going to be corrupted by some Gaussian noise with those characteristics there. So 0 mean and a standard deviation of 0.01. So not a lot. Okay? So observations from 2 points on the domain. And what we want to do is we want to solve the inverse problem. We want to get the distribution for kappa given the data that we're going to observe at these two locations. So we're going to do it in two ways. We're going to do it the sort of standard way, where we'll just pick a numerical solver from NumPy, plug in the value, ignore the fact that there's any uncertainty associated with it, and then get the posterior distribution for kappa given y. The second way we're going to do it is we're now going to take a probabilistic numerics approach to solving for u, get that probability distribution, and induce a posterior over kappa, which incorporates that uncertainty. And here are what the results look like, and I showed you them yesterday. So in the first case, where we don't account for uncertainty in the numerical procedure, we get something that looks like this. And so what you can see is that as the number of data points increases, then we get the theoretical consistency which we would expect. Okay? So we can see that pi of kappa given y is contracting to this Dirac on the actual generating solution, generating value, which is kappa equals 1. Okay, so you can see the consistency as n increases, right? And in the probabilistic case, you can see exactly the same. You can see that it is consistent, that as n increases, then we converge to a mean which takes on the value of the true generating value, kappa equals 1, and you can see that the variance is shrinking. And so if if we just piled on the number of data points, you would see that this would just start to shrink to basically nothing. But the point that was made yesterday in motivating this work was that in the case where we don't take into account the numerical uncertainty, then what you can see is that although this is consistent, we have inconsistency in our covariance. So you can see that in the regime where we have a small number of data points, the estimate is saying, well, I believe the mean is down here, and I'm fairly certain about it. Now, this is pretty catastrophic, because what this is saying is that if we were to do a hypothesis test, then the actual generating value would not pass, any values in this region here would just not pass that hypothesis test. And this is a serious issue in terms of probabilistic reasoning, okay? Whereas, in the case where we have taken into account the uncertainty via probabilistic numerical methods, then we can see that, even at low values of n, what you can see is that the uncertainty is greater. And as the bias decreases, because we observe more data, then the certainty starts to increase, or the uncertainty starts to decrease. And it does so in a manner which, if we were to be thinking down here and doing hypothesis tests, it would still give some credibility to this region here where the true value happens to be. And this is good. On the other hand, here it doesn't. The other danger, of course, is that you could look at this solution and say, well, the variance is actually quite low, so I probably don't need to invest any more computational effort. I'll stop here. And this is disastrous. Whereas here, we can see that, wow, we've got quite a wide error band here. Maybe if we invest some more computational effort, we can reduce this and not stop at this region here. So this is a contrived example. It's a very simple example, but it's been contrived in such a way and made simple in such a way that we can see very clearly the impact of being able to propagate uncertainty through a pipeline, in this case a very small pipeline with two components, solving the forward problem, solving the inverse problem, and how the accounting of that uncertainty ensures that we don't fall into any unwarranted confidence about the actual solutions that we have. Does anyone have any questions or want to make any points about that? Yes? From the data. So in the normal case, in the standard case, the noise is coming from the error associated with the data. In the probabilistic case, the noise is coming from the error in the data plus the error, the probabilistic representation of the error, too far away, in the forward problem. So there are two sources. In the probabilistic case, there is only one source in the usual case. So the usual case, you would always take into account the uncertainty due to measurement error or measurement noise. And you would consider this to be fixed. Here, what we're saying is that this is in actual fact associated with a probability measure, and in this case here, we can marginalize it, and what you see are the two sources of uncertainty here. One associated with the measurement error, and the other associated with the numerical error. Yes? Yeah, so that's a very good observation. Clearly someone's awake. What you see here is n, the number of data points, measurement points. So we've held fixed the number of points in the domain where we've probed the values of g, the right-hand side function. And so, you know, this will always then represent that residual error. So for this to go right down to a Dirac, then of course the other one has to increase as well. Good point. Yes?
So the error bars on the left side are representing, or the differentiation error bars on the right and left diagram. They are numerical error.
Yeah, so the difference between the two is that on the right-hand side, the error bars are defined by this. And on the left-hand side, the error bars are represented by this plus this. Where? Yes, so as I said, this is a contrived example, and the reason that this is so large is just to make the point. But also, if the numerical error, I can't remember how many, I don't recall how many grid points we were using, but it was fairly coarse anyway. Yeah.
So you're defining the grid points as your sample point, as n you also...
No. Here we only kept, so here we kept the number of evaluations of G fixed, and what we did is we increased n, oops, going the wrong way. We increased the number of observations of Y. Where are we? So we increased these yi values. Any questions from this side? Yeah, so very good question. So could we increase the rate of convergence by, in some smart way, selecting where we would make the, where we would make the data points? And the answer is yes. And this is another good example of why a probabilistic approach to numerical methods can be advantageous. In statistical methodology, there is a technique called experimental design. And in fact, I noticed that there's a poster from the summer school on experimental design. Who owns the poster on experimental design? Okay. Oh, both of you, right? So that's why you asked the question. So we can do exactly the same with this here, as we can use experimental design procedure to get a design that would be optimal for the PDE that we want to solve. And in fact, in some slides just to follow, you'll actually see that in action, where we take an initial sampling protocol, and we then use some experimental design and we improve that protocol. Good point. Now, again, that's something that emerges very naturally from the fact that you now are employing probabilistic semantics and statistical machinery, so likelihoods and priors. And experiment design, and optimal experiment design, just emerges naturally as another tool that you can take out of the toolbox because we have now placed this statistical framework around the problem. Any other questions? Yes? Yes, and that's exactly what that's exactly what we do. So in this case here, we only have. So this is a bit confusing actually. So these ends are repeated measurements at the same two locations. Okay? Very good. Let's carry on. Let me give you just an example. So moving away from the nice synthetic toy examples that are illustrative to some more interesting ones. And I mentioned that this fairly simple linear PDE that I've chosen as an example to work on is used in a number of settings. It appears in a number of settings, and one is in electrical impedance tomography. And EIT has been used and is being used as a medical imaging technique. And in this case here, what we want to do is we want to use EIT technology in an inverse problem setting where we would have a patient, we would basically use some electrical signals and you know, pass them through the body, and given the measured responses, what we would like to do is reconstruct the conductivity field within the patient's body. And then by doing that reconstruction, we can build an image of what is going on within the area or the volume that's actually being looked at. So this is very much an inverse problem. And the construction is such that, you know, imagine that we have some contained body, right, so just represented by this circle, and there's stuff inside, and what we're interested in is this kind of blue blob here, which could be something that we want to identify. And the working hypothesis is that this will have a different conductivity from the surrounding material. So what we can do is we can inject patterns of electrical current into this particular body. And so what you see here are on the surface of the body a number of electrodes on the boundary, and in essence what they will do is pass a current, at that particular location through the domain of the body. Okay, so we'll have a number of particular patterns of current which would be injected at particular locations through these electrodes. And the response, the measured response to those patterns is the data that we're going to use to try and infer what shape the blob is and where it is. So in essence, the data would be constructed of the voltages that would be measured, okay, at the electrode locations. And in essence, we take away some reference. The key point, again, is that this data is going to be measured with some error. And that error, we happen to know what its statistical properties are. Okay, so the conductivity field looks or is represented by, you should be familiar now with this elliptic partial differential equation. Okay, so these are the voltages, these are the conductivities that we're interested in, and then these are just some von Neumann boundary conditions that have to be satisfied at each of the electrode locations. So here's the experimental setup. It looks like a big cooking pot with 3 bits of fat in it. And so in essence what we've got is we've got this saline tank, and we have, you know, these 3 objects, and they've been fashioned to look like a pair of lungs and a heart. And the thing here is that the 3 solid objects will have different conductivity from the surrounding saline, and furthermore, the object, the rounder object, which is meant to represent the heart, has a higher conductivity than the 2 sort of lung-shaped blobs as well. So there's going to be a number of electrodes, and in this case there are 32 of them, and they are just equally spaced around the tank. Again, we could, if we take a probabilistic perspective, we could avail ourselves to experiment design and understand what would be the best pattern of placement of electrodes to minimize the variability in the inferences that we make. Okay, so there are a number of stimulation patterns, and we make the measurements. The key point is that this is a reasonably high dimensional problem. Now, for those of you that are working in deep learning and so on, you're dealing with really high, very, very, ridiculously high dimensional problems. But in deep learning, you don't really care about statistics. You don't really care about uncertainty. And I think those that are finding it very challenging because of the high dimensions. And so although this is only 992 observations, it doesn't sound terribly high dimensional. It actually is very high dimensional and very challenging. So I guess one of the other points is that the data is weakly informative because of the location of where the sensors are, which is around the boundary. And the other point is that the target, so the conductivity is actually a function, and therefore it's infinite dimensional. And that in itself makes the problem even more challenging. And if I was to give another 3 lectures on, say, simulation-based inference or Markov chain Monte Carlo, I would talk about how do you simulate, how do you sample from Banach spaces, from function spaces, where the objects are intrinsically infinite dimensional. But I'm not going to do that. Just suffice to say that because this is an infinite dimensional object, the problem becomes that bit more challenging. And of course, the ideal likelihood, the ideal marginal likelihood of the observed or the measured voltage patterns would require the exact solution of the PDE, which, as we know, we can't solve. So we use the machinery that we've just introduced and use the probabilistic numerics likelihood. And then we crack on. We do use Markov chain Monte Carlo, and we do use Markov chain Monte Carlo for functional objects, so infinite dimensional objects. Again, I won't bore you with the details of that, but there's a whole suite of machinery that allows us to do that reasonably painlessly. And hopefully you can see what the posterior means of the conductivity field look like as we increase the number of data points. I don't know if that's clear. Is it clear on the screens? Yeah, it's not bad, is it? So what you can see is that the posterior mean has clearly identified 2 lobes which have a lower conductivity than this heart-shaped component, this round-shaped component, and both of those lobes seem to have a posterior mean conductivity which is pretty much the same. So in terms of the reconstructing the actual unknown conductivity field, it seems to be doing quite a reasonable job. And again, if we look at the variance associated with it, in essence, the way to interpret this is that the variance associated with the region which has the higher conductivity is lower than the variance associated with the 2 lobes which have got a lower conductivity. And that kind of intuitively makes sense because there's more information about the higher conductivity because it has a greater interaction with the actual patterns of current that have been injected through it. Now, that is an actual example which has been used in the literature. We've published it just recently on an actual experiment, and it's a reasonable example. Let me just close this by giving you one final example where up until now we've basically spoken about probabilistic numerics where the operator, so in this case the partial differential equation is linear and everything goes through nice and analytically. Now the reality is in a large number of cases the governing PDEs are typically nonlinear, and here's an example here of a nonlinear PDE. So you can see that u of x is actually raised to the power of 3 in this example, but we have a linear diffusion term and a linear term here, but we've got this nonlinear term. And what's interesting about this example is that you actually have 3 solutions. So there is no one unique solution. And this is a very well-studied system. So if we take this as an example and do a probabilistic numerics, or give it a probabilistic numerics treatment, then I would need another 3 lectures to describe how we do it, because we have to resort to, oops, I didn't make this, just realized that. Because we have to resort to Markov chain Monte Carlo methodology. And in answering your question about changing the initial, the designs, here is an example. This example here is one where we had an initial design. So in other words, we selected a number of points in the domain where we evaluated the right-hand side and then used those to get the posterior over the solutions. And given that, we can actually obtain an optimal design, which is different. And you can see that the quality of the solution is much improved. And it's much improved just simply because of the design. So where have we decided to take observations in the domain? So again, I think this is another quite compelling reason as to why a probabilistic approach should be taken, because without any effort at all, we can then start thinking about things like optimal designs or optimal segmentations of the actual space. And the inverse problem, again, looks pretty similar. Another example is time-evolving systems. So the systems that we've looked at have been steady state. We can have these parabolic systems where there is now a time component associated with it. And again, I won't go through the details, but we can construct probabilistic solvers for these types of problems. And the example that I've got here is a way in which we can model burglary, and burglary in London. And the way it's described is by a system of 2 partial differential equations, one describing the amount of burglary that's taking place, and the other describing how attractive a particular region is for burglars to decide to actually move into that area and to do something. So these are the nonlinear PDEs, and if we just look at a very simple example as time evolves, then what we see is the attractiveness, so the attractiveness of a particular area to criminal behavior, and then the actual density, the actual amount of criminal activity that's taking place. Now, if we solve these non-probabilistically, you would just get one solution and we'd be done. But what we're getting here and what you're seeing is the uncertainty associated with multiple realizations. And you can see that the kind of hot spots down here, they're not individual. It doesn't look like these are individual hot spots. So there's a fair amount of uncertainty about the hot spots down here. Whereas here, it is fairly certain that these are hot spots for criminal activity. Whereas this here, it looks like the uncertainty would suggest that, these may not necessarily be hotspots that are supported by evidence. Yes? It's not periodic, it's just periodic. Okay, so that's an hour, so I've got half an hour now to go through integration. So I'm going to leave partial differential equations, and I'm now going to go into integration. And integration is probably one of the most important operations that is done in machine learning. It appears everywhere, and it appears in the form of a means of taking expectations with respect to some sort of measure of interest. And this is an example where you will see that a probabilistic approach to integration can actually provide us with the opportunity to exploit this additional mathematical structure and obtain algorithms which are superior in the sense that we can improve upon rates of convergence. So say the Monte Carlo 1 over root n rate of convergence. So I'm going to present this work to you, and we've got about 25 minutes left. So I'm going to make a suggestion. I can either start this now, stop it, and then continue tomorrow, or we could break, or we could have a question session now, and then that would give you an extra 15 minutes before I don't know what happens next, before the poster session. Hopefully there's going to be some beer at the poster session. So what do you want to do? Do you want to have a question? This is a nice kind of logical break point. So we could either start on integration now, and I could drone on for another 25 minutes, or we could have a Q&A session which would last for, say, 10 minutes, and then we could all scurry down to the poster session. Hands up for me continuing. Hands up for a Q&A and scurrying down for the beers. Well, it looks like you want to hear me continue. So we'll continue. Okay, so integration. The example that I'm going to give you is not a straightforward one, because we're going to integrate over a manifold. And the application is one from computer graphics, where we would take an object, right, so some object, and we want to embed that object into an environment. Okay, so we've got some object, and we want to plop that object into an environment. And what we want to do is we want to render the reflections on that object in such a way that it is representative of the environment that it has been embedded in. And so what that means that we have to do is that we have to look at the reflectance of the light sources within the environment map and how they are actually So here's our environment, okay? The light is going to be reflected off the object onto the actual observation, so let's call it some camera. And in essence, what we need to do is we need to compute a number of kind of reflectance integrals for each point on the object. So in other words, if we're dealing with red, green, and blue channels, for every pixel in the environment map, right, we're going to have to compute these three integrals here. And the integrals look something like this. I mean, this is not really important. What's important is that for every pixel in the image, we've got three integrals that we need to compute, okay? Based on the outgoing radiance, the amount of light that's emitted, the amount of light that actually reaches the object that we want to embed, and so on. But the key point here is that we're going to be integrating this, right, with respect to this probability measure here, which is a uniform distribution on the object that we're going to be embedding, which is going to be a sphere. And so therefore, the manifold that we're dealing with is S2, okay? So it's the two-dimensional manifold, the sphere, embedded in 3D space. And what needs to be computed is this integral L0 for each pixel and for each RGB channel. And so the question is, can we do it efficiently? Because we can't compute this integral analytically, so we need to do it numerically. Yeah, can we do it in a consistent and a reasonably rapid manner? So that's what we want to do. We want, for a particular function f, which is continuous and square integrable, and a probability measure pi on some domain, which is a Rd, then we're going to use this notation that pi square brackets of f is basically just the operation of this integral with respect to this measure acting on this function f here. And the standard numerical approach is to take a number of function evaluations, a certain number of points in the domain x, obtain a number of weights, often called quadrature or cubature weights, wi, and weight the function evaluations, and then just take the sum of these. And that will give us our approximated or empirical integral here. The other way you can think about this is that we're taking the integral with respect to some empirical measure, pi. Now, if the value of the function, right, if obtaining the value of the function is expensive, then we're not going to be evaluating the function a large number of times. Now, it may well be that the function could be the forward solve of a global weather system model, which might take quite a considerable amount of time. So we don't want to evaluate that a whole load of times. So in other words, n is going to be small, and n is small because f is expensive. So we would have high numerical uncertainty in this situation here. And so the probabilistic numerical solution is what's called Bayesian quadrature. Now, Bayesian quadrature is very interesting. It was called Bayesian Monte Carlo in the machine learning literature. So there was a NIPS paper by Carroll and Zubin in 2002 where they reinvented Bayesian quadrature, unknown to them at the time, called it Bayesian Monte Carlo, and showed that you got better rates of convergence than standard Monte Carlo. And the rationale was, well, it's Bayesian, so it must be better. But there was no real in-depth analysis as to why that should be the case. And as I said, O'Hagan had actually looked at Bayesian quadrature, 10 years before. And if you remember, Larkin in the late 60s and early 70s had actually solved this problem before either Tony O'Hagan or Karl and Zubin appeared on the scene. One of my PhD students, Briol, just recently published some work where we actually mathematically do the analysis so that we understand why and in what cases a Bayesian or a probabilistic numerical solution, a Bayesian quadrature solution, would actually have increased rates of convergence over standard Monte Carlo, and what those rates of convergence are and what they depend on. So, so there are some nice papers from my group, well, I would say that, wouldn't I, on this particular problem. But the construction here is fairly straightforward. We put, oh, that's me. We put a prior measure on the function, so on the integrand, and because the integration with respect to this measure, with respect to whatever the measure happens to be, is linear, then we can just push forward the prior measure on the function to a measure on the value of the integral. So the maths is actually fairly straightforward in devising the actual numerical procedure. And again, because you had a very nice lecture today on Gaussian processes, you're all experts and you all understand the machinery of Gaussian processes. So I'm only going to use one slide to describe it. But basically, what we do is we say, we've got a function, so we have an integrand, right, represented by this red function here. And we are going to put a zero mean Gaussian process prior on the value of the function, which is the integrand. We can then push that forward via the weighted integral operator, which is linear, and that will induce a posterior distribution over the actual value of the integral of that function with respect to whatever the weighting measure happens to be. And so what you can see is that if we have 0 data points, so 0 evaluations of our integral, and we just push forward the prior Gaussian process, then the posterior over the integral value is, well, pretty flat, because there's no information at all. If we evaluate the integrand at 3 points, 1, 2, 3, then you saw the nice charts today on Gaussian process function approximation, where in the noiseless case, we have this interpolant whose mean looks like this, and the uncertainty associated with it looks like this here. So clearly in the noiseless case, there is 0 uncertainty around the mean values at these 3 points, but the interpolants are going to have a certain level of uncertainty. Again, we just push that forward, so the posterior on the integrand, we just push it forward to get a posterior on our integral. And now you can see that with 3 data points, we start to get a distribution whose mean is biased, but you know the high density regions cover the true integral value. And if we up that to 6 evaluations of the integrand, push it forward, then we can start to see the contraction of the posterior and the removal of the bias, to some extent anyway, of the actual value of the integral. And the mean, the posterior mean function for n evaluations just looks like this here, which again is exactly what you saw this morning. The variance, again, looks, or the predictive variance, or the interpolation variance, looks exactly like what you saw this morning, with the exception of the fact that we have an operator pi, the integration operator, which will now appear in the representations of the mean function and the interpolation variance. And what you see is that the covariance function here is now acted upon by this operator. So in other words, what we need to be able to do is to analytically integrate the covariance function with respect to the measure of interest. And if we can do that, this would be the representer, then we're done. Now that's a big if, because there are, well, there's a small number of covariance functions that would allow us to obtain this type of integral analytically. And indeed, if the integral is with respect to some weighting measure, pi, then that class of covariance functions, which would be integrable analytically, may be even smaller. So the first thing to note is that although this is a very nice result, its application may be extremely limited, because we need to have a covariance function that can be analytically integrated. Now, in the second part of this lecture, I will talk about probabilistic methods where the required integrals cannot be obtained analytically, and how we can still construct probabilistic integration schemes. Yeah. Yeah, so the W's are in fact, so if you look at this here, right, so we've basically got a weighted sum of the function of the integrand evaluations, and what you see here is exactly the same. We've got a weighted sum of the evaluations of the integrand. So the WI's come from the choice of the covariance operator and the choice of the abscissa at which so the points at which you evaluate the integrand. So that's where the W's come from. Okay, so that seems fairly straightforward. And I'm sure there's plenty of you that are absolutely itching to pull out your PyML or whatever it is, your Python, and actually write a little script that allows you to do this. But let's just look at a little bit of the theory associated with this. So the first thing is that we are dealing with functions which are going to have a certain level of differentiability, and therefore we are dealing with reproducing kernel Hilbert spaces, Sobolev style function spaces, which define the levels of smoothness. So again, we saw this today regarding the differentiability of the functions of interest. So the inner products and the associated norms are going to be defined by the L2 norms or the L2 inner products of the derivatives, or sum of the L2 based norms and associated derivatives, inner products, sorry, of the various derivatives associated with the function class. And the way that we can study the performance of the Bayesian integration method is by looking at the sup norm between the actual integral and the mean, the posterior mean of the procedure. And it turns out that the rate of convergence of the mean is of order 1 over n to the alpha, where alpha is the level of smoothness of the function class, so the number of derivatives, and d is the dimensionality of the space. So let's just take a one-dimensional integral, just for the time being. Then we can see that the error, or the rate of convergence of the error, will increase as the smoothness of the integrand increases. And this is one of the insights that we never really got from the machine learning literature. As I said, it was just an empirical observation that you know, for the examples that were given in the NIPS paper, you got better convergence than Monte Carlo. And the reason for that is because of the smoothness, the level of smoothness of the functions. The smoother the function, the higher the rate of convergence. So that's the first thing. Have I got time to go through this now? Yeah, I'll just close with this here. There's going to be a bit more analysis in the next lecture. Okay, so this is all very nice. Now, I'm going back to integrals over manifolds, and if I've got time tomorrow, I'm going to present this work in the general case where I'm not thinking of a Euclidean space, but I'm going to define it on, you know, some sort of manifold structure. And the example that we've given here is we're going to define a Cameron-Martin, a reproducing kernel Hilbert space of which map from S2, the sphere, onto the reals, and the kernel, the covariance function that would lead to a Sobolev space of smoothness 3 over 2, which actually turns out to be optimal for S2, is this little operator here, this covariance function here. Okay? Now, just take my word for it that there is a place in heaven where these covariance functions come from for manifolds. So we're going to use this covariance function, and we're also going to use a design, so where we're going to select the points on the sphere so that we get a convergence rate which is of order n to the 1 over n to the the 3/4, which turns out to be optimal as it happens. And the results look something like this. So if I just look at one example, one pixel for the red, green, and blue channels, the little black line is the Monte Carlo estimate, and it looks fine. As the number of states, as the number of quadrature points increases, then it kind of converges, so that looks good. But if we take the Bayesian perspective, the Bayesian quadrature perspective, and we exploit the fact that we know the smoothness of the functions that we're trying to integrate, we can then define a class of covariance function and therefore the appropriate space of functions. We get a procedure that looks like this. So you can see that the rate of convergence is much quicker. It's much more consistent as well. You can see the uncertainty shrinking quite rapidly and consistently, which is quite nice. And as I said, for this particular space on S2, then we are able to achieve the optimal rates of convergence. Now this is kind of cool because this is a very generic framework, and in this case here, we are able to beat the Monte Carlo scheme, which of course is unsurprising because we are exploiting the mathematical structure of the space of functions. And in the lecture that I'll give tomorrow, we will exploit not only the structure associated with the space of functions, but the space of the probability measures as well. And we will define reproducing kernel Hilbert spaces that takes into account the space of functions and the space of probability measures. And we'll look at the rates of convergence, and empirically, we'll look at some of the sorts of results that we can obtain. So I think that's us. Beer awaits us, I hope. And what we'll start on tomorrow is integration with intractable densities. So this is integration where we cannot analytically obtain the representers. So we cannot integrate the covariance functions. I'll close there. Yeah, we're getting thrown out. So I'm finished.